Let's pick up where we left off. So, mention the discharge, the hydraulic conductivity, and the hydraulic gradient, which is basically the slope of the water table or the slope of the pressure surface for a confined aquifer. And as you might imagine, the steeper the slope, the faster the water goes. So, the greater the permeability, the faster the water goes. The steeper the slope, the faster the water goes. A in Darcy's law, because this is a volume issue, is the cross-sectional area that the water is passing through. Now, this could be the area of a screened well. It could be the area just of an aquifer, like what's passing under somebody's property or through a river valley. There are a lot of different things that you could use for area when you're trying to do the volume. You do the math, what you find out is that the rate of flow is really, really slow. The volume of water, however, can be quite large because we can be looking at pretty large areas through which the water is flowing. But the rate of flow is going to be inches or centimeters per day at best. So the water just naturally flows very slowly. If we want to just calculate the velocity, we simply take the cross-sectional area out and we multiply the hydraulic conductivity by the hydraulic gradient. The residence time is just the amount of time that water spends in the ground from the time it falls down as rain until the time that it's discharged to a stream. And typically that is on the order of thousands, in some cases tens of thousands of years for water to flow through the system. So this residence time and the storage of groundwater, you can look at some pretty large amounts of time. What that also means in terms of sustainability is that because the water is moving very slowly, in some areas where you don't get a lot of rainfall, we'll see that you can actually tap out the groundwater, basically lower the water table and use up what's been stored. So these are some numbers from your book just to give you an idea of why this is so slow. The hydraulic conductivity is our key number here. And you can see that in clay it's very low. That's why we usually classify clay as an aquitard. You can see that's really one of the lowest numbers on here. And then to get numbers that low, you have to have a dense crystalline rock. On the sedimentary side, it's something like limestone or shale. And then on the igneous rock side, it's going to be something like granite. And you can see those numbers are really super low. But they're not zeroed, which is why we don't use aquiclude as a term. On the other hand, on the upside, you can see that sand and gravel or a mixture of those are going to have relatively high hydraulic conductivities, and those are going to be the units that serve as aquifers. And it really comes down to the permeability or the hydraulic conductivity. You'll notice over here on the porosity side, clay can be 50% open space, and yet with this low hydraulic conductivity, that's telling us those open spaces are not connected, which makes it very difficult for the water to flow through that material. So it's important to understand the difference between porosity, which is your open space, and the conductivity or the permeability measurement, which is the connections between those open spaces. One example I like to use is a building like the college has a lot of open space. If you think about floor space compared to space occupied by the walls, you're looking at 90 to 95% porosity. However, the permeability depends on whether or not the doors are open and unlocked. If you close and lock all the doors, the college is not very permeable. You can't go from one room to the next. And so flow of people in that case is shut off if you close and lock the doors. And so that's the difference between porosity, which is just how much open space is there, and permeability, the measure of which is hydraulic conductivity on this chart, which is how connected are those spaces? How easy is it to get from one space to the next? So the next concept, and this actually comes, we're doing this in a certain order, this comes from our groundwater flow equation, it turns out, and we'll talk about this more in lab when I can draw it up on the board and get into more details. But basically, when you start pulling water out of a well, it lowers the water table directly around the well. And what's happening here is you're pulling out the water initially faster than it can be replaced. And so the water table drops down. But when the water table drops down, you'll notice it gets very steep around the well. So we actually change the hydraulic conductivity, the hydraulic gradient number, this H over L. This goes from shallow or kind of flat to steep. And when you increase this number, you're going to increase the flow of groundwater. You also start pulling water in from all sides of the well, and so your area in this calculation is going to be the area of the outside of the cylinder of the well. And so the cone of depression, if you're doing it right, so if you are in an area where you're pulling the water out in a sustainable way, that cone of depression will develop, but it will then stabilize and stay pretty much the same year round. It may go up and down a little bit with the seasons, but it'll stay pretty much the same. If you take out too much water, what will happen is the cone of depression will just keep getting bigger and bigger and deeper until eventually the well goes dry because you're just taking the water out faster than it can be replaced, even with the steep gradient of the cone of depression. So that's why the cone of depression is important, and that diagram is important. We've already mentioned artesian wells, which are flowing wells. But if you have a flowing well, what will happen in that case is it will reduce the pressure gradient around the well, or reduce the pressure around the well, and the gradient will increase potentially a little bit. So what we need to do with this water supply is we need to compare our yield to the amount of water that's being replaced by recharge from the rain. And so if our extraction equals or is less than the rain that's falling in the area or the recharge, then we would consider our yield sustainable. We're not taking out more than nature is replacing with rain. On the other hand, if we're in a very dry area and we're pulling out more water than rain replaces, we refer to that as groundwater mining. That is not sustainable over the long term. And what we'll see happen is this. The western United States is dry. There's a wonderful aquifer there. It's called the Ogallala Aquifer. It's a very thick sandstone, has a lot of water in it, but you'll notice the groundwater overdraft, which is the excess that's being taken out compared to the rain that falls, is very serious in some of the western United States. In the California Central Valley, in the area of southern Arizona around Phoenix, and then in the high plains on the Ogallala Aquifer. And if we focus in on the high plains, we see what has happened because of this overdraft. Water level changes from 1940. I think this was drawn in the early 2000s, so this is like 20 years ago. So over the course of about 60 years, the water table dropped in some places by over 50 feet. So that is significant groundwater mining. When you take that much water out of the ground, in some places the ground surface actually drops down because the pore spaces that had water in them collapse and you get surface subsidence. So that is the risk of overusing or using the groundwater faster than nature is replacing it. So that leads us to groundwater surface water interaction. We've mentioned this already, but we have gaining and losing streams. In Illinois, our streams are pretty much all gaining streams, which means they gain water from the groundwater system. Lake Michigan gains water from the local groundwater system. And when water comes directly out of the ground, we refer to that as a spring. Now, if the bedrock is made of material that can dissolve easily, we can get caves and sinkholes when those caves collapse. And we mentioned subsidence in class a few weeks ago as one of our hazards. In our area, subsidence is due primarily to mine collapse. But there are other places, even in Illinois, in southern Illinois, where the bedrock is made out of limestone. And because the bedrock is made out of limestone, caves form as the limestone dissolves. And when the cave gets big enough, the roof can collapse and you can get what's called a sinkhole on the surface. And so this is a picture of an area that has some sinkholes, and this is what it looks like if you go down into the cave. So the last few slides we have are about water supply and water use in general. We've already mentioned the input from rain and the output from runoff, withdrawal, etc. If there is a drought, that just means that we're not getting the normal amount of rain. Some areas just have a low amount of rain anyway, and if they go into a drought, things can get really desperate. So what does water use look like in the United States? Well, every 5 years, the U.S. Geological Survey puts out a new publication showing water use in the U.S. And the good news is, even though our population is going up, we're getting more efficient with our water use. You'll notice that our total water use has been declining for the last 10, really 15 years, because this goes back to 2005. You'll notice the total use went up till we got to 1980. It kind of leveled off till 2005, and it's been dropping ever since. And this is because we're becoming much more efficient in our water use. Now, that doesn't mean that we're in the clear yet. Some areas, as we saw in that last map, are still overdrawing their resource. Where does that water go? Purple is public water supply, so that's city water, and that's used by both industry and private houses. The red here is rural, domestic, and livestock, so that's what farmers use to drink and shower and stuff in the house. That would include me and my little farm well and what they use to feed livestock. Irrigation, you'll notice, is one of our biggest users here. That's the green one. And the big yellow one is thermoelectric power. Now, if you're wondering what that is, that's kind of an interesting use. That is the water that we use in electric generation at a power plant that heats the water up, uses that hot water or steam to drive turbines, and then lets it cool off. So LaSalle Nuclear Power Plant, for example, has these big lakes where they hold water to cool their process, and they also have water that runs through the turbines. Now, the interesting and important thing to note about thermoelectric power water is that it is what we call a non-consumptive use. So when the power plant's done with it, they put it back, and they haven't actually used much of it. So they're able to put it back. Agriculture, for example, irrigation, the green bar here, is what we would call a consumptive use. Once you put the water on the field and the plants use it, it is not going back where you got it. So it's important to distinguish between consumptive and non-consumptive uses. And this overview slide just kind of breaks those users out into different groups. It shows you the big users again. Irrigation here, that's a consumptive use. Public supply is a consumptive use. And then thermoelectric, generally not a consumptive use. There's just a few more slides. There'll be another really short narrated PowerPoint for you to look at with those slides.